Hey, today we're going to talk about light. It's got this split personality. It's got two identities. It's not quite sure what it wants to be. What we mean by this is commonly referred to as the dual nature of light, meaning light can behave as a wave, but it can also behave like a particle, like it's dust, like it has mass. And that's what we're saying here is basically when we say it acts like a wave, we're saying it's massless. And when we say it's acting like a particle, that means it acts like it's got mass, like we could weigh it. Um, and we're going to go over those reasons why we say those things. First, light is a wave. Not like it's mass light, but like light, sunlight, radio waves are light, electromagnetic waves. The first thing we want you to know about light is that it's a transverse wave, all right, which means it's going to be traveling like this. Um, Light does not require a medium. That's why we call it an electromagnetic wave. You could see an explosion in outer space, but you wouldn't hear it. But you would see it because it does not require a medium. So the light would travel across the space, and you would see it. Well, how do we define light to be a wave? Well, there's four rules or four things that have to happen for us to identify something as being a wave. First of all, does it show interference? And yes, it does. All right, light does have interference. Um, does light reflect? Well, we know that light reflects. It'll bounce off of a mirror. Does light refract? Well, we've all seen the glass where you stick the pencil in there in the water and it seems to change direction. Will light diffract? Well, in class we've shown video and I've shown I shut the door and we had the light coming in from outside and we did find indeed that the light diffracted. So light can be defined as a wave, but there's sometimes when that definition doesn't necessarily fit everything that we see. But before we get into that, let's continue talking about light as a wave. Oh, sorry. Let's backtrack, and now we are going to talk about it being a particle. Light as a stream of particles. So what we're saying here is this is when it acts like it has mass. Uh, it acts like it has mass. That's the key word, is it acts. Sometimes people act differently than what they are, but that doesn't mean that's who they are. And that's the same thing with light. It doesn't have mass, but it acts like it does at times. The energy of light is contained in packets called photons. Well, what is a photon? A photon is a very small unit or quantum of light. Why? Huh? What? How? Huh? Well, here's what we know. Sometimes when you have very dim blue light strikes a metal surface, uh, sparks are shot off. How does that happen? Well, it acts like it's a particle. It acts like things are hitting the metal, and it's shooting off sparks. It's acting like it has mass. Light can be blocked by an object. We have a shadow. All right, you can stick your hand up and block the light. In those instances, light's acting like it has mass. I can't block a radio wave with my hand, but I can block a light wave with my hand. So it's in those instances that we say light acts like a mass. I mean, just the pure fact of shadows is a reason to say that light acts like a mass from time to time. Photons. Photons are particles. Photons do not have mass. Um, Photons have energy in a very specific small area. So photons, they are particles, but they don't have mass. That there's one of the hardest things for kids to get around is how can something be a particle but not have any mass? And it's a particle because it's a lot of energy, but there is no mass. Let's look at the electromagnetic spectrum. All right. We're going to talk about some things we've talked quite a bit over the last couple days, and the electromagnetic spectrum is all the lights. All right, this is all called light. This is all called light. These are all light waves. Even though it's radio waves, microwaves, infrared waves, white light, ultraviolet, X-rays, and gamma rays. These are all called light. All right, light is it's all light waves. Um, there's some characteristics we're going to talk about here. First of all, let's talk about wavelength. All right, wavelength. When we look at the left side of the electromagnetic spectrum, radio waves, microwaves, infrared, these all have longer wavelengths. As we start to head to the right, gamma waves, they have shorter wavelengths. One of the things we've said this week is that frequency and wavelength are inverses of each other. So if wavelength is long or is big, then the frequency is going to be low. The radio wave, in this case, a radio wave is really long. So its frequency, it's not going to have a lot of vibrations. All right. Or to its counterpart here, a gamma wave has a very short wavelength. A gamma wave has a very short wavelength. So it has a very high frequency. If you notice, there'd be lots of vibrations here. There's lots of very high frequency. Well, things that we've learned. Two things. If you have a short wavelength, you have high amounts of energy. So short wavelengths have high amounts of energy. Likewise, if you have a high frequency, you have a high amount of energy. So what we see here then when it comes to wavelength, as we move to the right, the wavelength gets shorter. As we move to the right, the frequency is going to become higher. And then with that as well, energy as we move to the right is also going to get higher. Alright, last slide for the day. Here's an example of this. Notice that we have a long wavelength, very small frequency. They're inverses of each other. As the wavelength is long, the frequency is short. Wavelength gets a little longer. The wavelength gets a little shorter, so the frequency gets a little bigger. When the wavelength is really small, we have a very big frequency. And you can see that over here, small wavelength, but a lot of frequency. So these two, wavelength and wave frequency, are inverses. These two right here are inverses. And then wave frequency and photon energy, these are what we call directly related to each other. Meaning, if the frequency gets bigger, so does the energy. All right. If the frequency gets smaller, then so does the energy. Well, hey, hope that's been informational for you today. I'll catch you on the flip side.